Hello everyone. Uh, in some of the previous lectures, we have been discussing the notion of equivalence relations, and in the previous one, we discussed this group Z mod and Z, right? And we also discussed certain results, and that given an equivalence relation on a set S, the two equivalence classes. Hmm, just give me a moment. Yeah, the two equivalence classes are neither disjoint or equal. So if you take if you take two equivalence classes, the intersection has to be either empty, and if the intersection is non-empty, then they have to be equal. Uh, yeah. And then we define this composition law on Z mod nz. More precisely, we define the map from Z mod nz cross Z mod nz to Z mod nz. And we define it as follows. You take two equivalence classes, C and D. There, this quote unquote the sum of C and D, which is denoted by C star D. It is defined as the equivalence classes of C plus D for some choice of C in C and some choice of D in D. And then the question was, does this equivalence class of C plus D depend on the choice of C and D from C and on the choice of the elements little c and little d from the equivalence classes capital C and capital D? So then in this lemma, we showed that this is not the case. It doesn't depend. So it is independent of the choices of these representatives. So this kind of choice of elements is something called representatives. Okay. So no matter what C and C prime we choose from C and what D and D prime we choose from D, the equivalence class of C plus D and the equivalence class of C prime plus D prime, they remains the same. Okay, and that was the basis of our our next theorem. Basis in the sense that it showed that the definition that we had it makes sense. That is, the composition law that we introduced is well defined. Once that is done, verifying that Z mod nz, that is the set of all congruence classes modulo n, forms a group under this composition law. Showing this statement was essentially straightforward. Okay, it was essentially formal verification. But again, this is something that we do need to do, and we did. So let's move on. Yeah, and here are certain notions and certain questions that I introduced. So are you familiar with another group containing exactly n elements? So try to come up with answers. You are indeed familiar. Okay, so let me tell you. So you are indeed familiar, but of course, here you have to indicate what is that another group. Okay. And now, yeah, there is a notion of order. So the number of elements of a group is called the order of G. This is usually denoted by G within these two vertical lines. Mm, yeah. Uh, Let me mention that this group Z mod nz will be appearing over and over again in this course. So please go through these arguments, and the notion of equivalence relation is of fundamental importance in mathematics, not only in group theory, but also in mathematics. Okay. So make sure that you understand it very well, or at least you understand the content that we have discussed so far. Though, sorry, maybe I should, yeah, the examples and the definitions of the definition, of course. Yeah, so since Z mod and Z happens to be one of the first one of the first somewhat abstract examples of a group, uh, so let me try to spend a while on that. You have you have already what to say yeah, you have already seen certain examples of groups. For instance, you have seen the example, you've already seen the example like maybe U2R, the example GL2R, or maybe even GLNR. You have also seen MNR. So they all, the first three form a group. Each of these first three forms a group under matrix multiplication, and this forms a group under addition of matrices, etc. Right? You also have seen the group S1. You have also seen the group C cross with respect to multiplication, and then R cross with respect to multiplication, etc. Right? Yeah, I mean, in some sense, this is concrete because I mean, you have seen matrices before, okay, so you didn't have any kind of trouble in visualizing what's going on. You have seen real numbers or maybe non-zero real numbers or non-zero complex numbers, and you've seen the circle before, okay. So there was not much, how to say, trouble in terms of abstraction or in terms of something new. Yeah, so Z mod and Z happens to be something really new. So just let me spend a while uh, to kind of elaborate it further. So let's work with Z mod 2Z. So what is Z mod 2Z? It is the set. Yeah, you may. I mean, okay, rather okay. So let me continue. Then I'll add one quote unquote correction. This is a set of the set of equivalence classes of the oops congruence modulo 2 relation on Z. So what you get is that, so this is a set, this is a set, right? Okay, so since this is a set, let's introduce the symbol of set first. Okay, maybe, sorry, I mean there is not much space to, god, just give me a moment. This looks better. Yeah, so since this is a set, oh sorry, since this is a set, so I have introduced the necessary symbol. So within this set, what do I need to write? Within this set, I need to put the equivalence classes, right? So let me write the equivalence classes then. Oops, sorry. So as I stated it earlier, I'll also explain it a bit. So I have to write 0 and then what? And then 2, minus 2, 3, minus 3, 4, minus 4, etc. That is a set of all even numbers, comma, the other element is what? This is 1, minus 1, 3. Oh, what did I do? I wrote 3 minus 3 before. Sorry, I was just getting, I just got carried away. I hope you have already, I mean, observed that what I was writing doesn't make any sense. I mean, that 3 minus 3 shouldn't have been put here anyway. So 3 minus 3 and then 5 minus 5 and then 7 minus 7, etc. Okay, so this is the set, and the correction that you may point out is that this is no more the set, this is the group. Or to be to be even more precise, just give me a moment, to be yeah, to be even more precise, we should say z mod 2z comma star. Okay, yeah, so this is the group. Okay, oops, so this is a group that we have already established. For z mod 3z, just give me a moment. No, this doesn't work. This will be current template. No. Yeah, so for z mod, for z mod 3z, so we will be having the set of all equivalence classes of the congruence modulo 3 relation on z, right? And I've already written it down, what happens, right? Somewhere, okay, this is not there in the notes. I wrote it down, I didn't type it beforehand. So let me just write things down for z mod 4z, okay? Yeah. So z mod 4z, by definition, this is equal to the set of equivalence classes of the congruence modulo 4 relation on Z. So this is a set, right? Within this set I have to write down the equivalence classes. Let's see whether I can. So I have to write 0, I hope I'm recording, yeah, 0, 4, minus 4, and then 8, minus 8, and then 12, minus 12. Writing this down is relatively easy. Writing the next one, I have to be careful. I shouldn't make a mess. Yeah, so let me add 1 to all of them. This should be 5, then this should be minus 3, this should be 9, then this should be minus 7, this should be 13, this should be minus 11, and then I have to do 2, and then 6, and then minus 2, and then 10, and then minus 6, and then mm, mm, uh, and then 10 plus 4 is 14, 6 and 4 is 10, etc. So it has to be it has to be 3, and then 7, and then minus 1. So and then 7 plus 4 is how much? Is 11, and this is minus 5, and then this is 15, and then this is minus 9, etc. I'm sorry if you are getting a bit bored. I mean, I didn't have much option. Okay, great. So this is Z mod 4Z, right? So I hope this makes you somewhat familiar with what we are doing. Okay. So yeah, so do remember that Z mod 4Z is the set. Okay. So you have, I mean, just don't write this, I mean, this sets only. So this sets has to be put within this curly brackets. This is something that I hope all of you understand, but again, this is something all of you need to be careful about. Okay. I mean, if you throw away this, if you throw away the set part, then I mean, then you are not describing Z mod 4Z correctly. And if it is not correct, then I mean, there is a room for improvement. So you have to write down the equivalence classes, and then you have to form the set using this equivalence classes, and that gives you Z mod 4Z. Okay. Yes, certain standard notations that I need to introduce. Yeah, maybe earlier you introduced the symbol CA and CB, right, to denote the so was that the notation from the very beginning? Maybe, yeah. So because CX was the notation, yeah. So for the equivalence classes of the, for the equivalence class of that element X, oops, sorry, for the equivalence class of the element X, that is the set of all elements of the set S which are related to X, or to which X is related. So that is denoted by CX. So following the same strategy, or following the same convention, we introduced, we denoted the equivalence classes of an integer a by CA. Okay, of course, by equivalence class I mean I have the equivalence classes with respect to congruence modulo n relation. You may say that where is n here? Yeah. Okay, so let me try to explain, because there is something subtle, something a bit subtle going on. It's only about notation. So for example, in this context, okay, in the context of Z mod 2Z, or in the context, more precisely in the context of considering congruence modulo 2 relation on Z, what is C0, for instance? What is C0, for instance? C0 consists of 0, and then 0, and then 2, and then minus 2, and then 4, and then minus 4, 6, minus 6, etc. Right? And here, when you are considering congruence modulo 4 relation, in that case, what is C0? In that case, C0 is equal to 0, and then 4, minus 4, and then 8, minus 8, and then what? 12, minus 12, etc. Right? So you see that C0 has changed, right? So this was earlier, this was a set of all multiples of 2, that is a set of all even numbers. So here you have the set of all multiples of 4, so a proper subset of this set, right? And this is not a surprise that C0 is changing, because this is the C0. Here C0, here C0 is the equivalence class of 0 under congruence modulo 2 relation, right? And this is the equivalence class of 0 under congruence modulo 4 relation. Okay, so you need to be careful. So this, there is some room for confusion, but this is a standard convention. I mean, we can also decide to write maybe some, I mean, maybe C, instead of writing CA, we may decide to write CN comma A, but that will only complicate the notations. Anyway, so try to write down Z mod 5Z, so that kind of, just to make sure that you understand this the equivalence classes of the congruence modulo n relation a bit better. Okay, you become comfortable with that. Okay, yeah, I mean, this is straightforward, but it is a good idea to do it at least once. And just few more notations to introduce. So it is customary to denote, I don't know which one to use, maybe red one. It is customary to denote this by 0 bar or maybe 2 bar or minus 2 bar. So so this is equal to 0 bar, okay, or maybe, I mean, okay, so what I fear is that do not write this kind of equalities within the set. This is not allowed, okay, or maybe I can try to rewrite it. So we have, oops, we have this 2, sorry, 0 2 minus 2, so this is denoted by 0 bar, and the next one 1 minus 1 3 minus 3, that is denoted by 1 bar. Okay, so this is the equivalence class of 1 is customarily denoted by 1 bar instead of denoting them by C0 and C1. Okay, so here, as you understand, or as you may guess, we will have 0 bar and then 1 bar and then 2 bar and then 3 bar, and this is very well equal to, for instance, 40 bar, and this is very well equal to 81 bar, this is very well equal to, this is very well equal to what? This is very well equal to maybe 102 bar, or maybe minus 98 bar, minus 98 bar, and then this is very well equal to maybe minus 9 this is very well equal to minus 997 bar, etc. Okay. Okay, great. So it's customary to use these letters. It's customary to denote, to denote the equivalence class of an integer a by the symbol a bar. Okay, so this group Z mod nz. This is a collection of certain equivalence classes. One can check that this is equal. I mean, this consists of only the n equivalence classes. This is something that sorry, why is it not working? Just give me a moment. Sorry, it just got hang. Okay, great. So it's working. Yeah. Yes. So there are n elements inside this group Z mod nz. Yeah, and I mean, one can show that that is equal to 0 bar and 1 bar and 2 bar and n minus 1 bar. This is something we have already stated in the previous lecture. Somewhere here. Yeah. Okay. I mean, we have stated it a bit differently. It states that the subset C1 up to Cn, that is the equivalence class of 1 2 3 4 till n, they're all the equivalence classes. In fact, they are all the distinct equivalence classes. So here you have got 1 bar, 2 bar, all the way till n bar. And in the next, today we are saying that instead of taking the equivalence classes from 1 up to n bar, you can take the equivalence classes of 1 bar, 2 bar, 3 bar, n minus 1 bar, and instead of writing n bar, I wrote 0 bar. Okay, and one can show that since n is related to 0 under this congruence modulo n relation, so the equivalence classes of n and 0, they are the same. Okay, or if you want, you can write that Cn is equal to C0, but you have decided to replace Ca by a bar, so that's why we have n bar equal to 0 bar. Anyway, and thus the composition law that we have on Z mod nz, that takes the following shape. As you see, that Ca star Cb, it was defined as Ca plus b. So instead of writing the symbol star, it makes much more sense if you use the usual notation for addition. Okay, that is the plus symbol. So that's what we will do. But again, this plus is not the plus that we knew. Yeah, so if you take two equivalence classes Ca and Cb, or as per our present convention, if you take two equivalence classes a bar and b bar, their sum is defined as the equivalence class of a plus b. There is some room for confusion here because the plus symbol appears twice, and these two pluses, they're different. Okay, so in what sense they're different? Let me indicate. So this denotes the addition, or let me write the composition law. This is the composition law on Z mod nz, and this is this denotes the addition of integers. Okay, so please be very careful. They look the same, but they're certainly not the same objects. Okay, they certainly are not the same operations. And so we have decided to use the letter star instead of we have decided to use the letter with the symbol plus instead of using the symbol star. So CA star CB. So we knew that CA star CB is CA plus B. That was the definition. So it takes the following shape, that A bar star B bar is A plus B bar, and we have decided to write plus for the symbol star, so it becomes A bar plus B bar equal to A plus B bar. Okay, anyway, so we just go through this over at least few times so that you become comfortable. Yeah, so far we have been just reviewing the notion of reviewing this group Z mod nz, and discussing certain conventions about this group. So let's discuss something a bit new. So this is there is a notion of cyclic subgroup generated by an element. Okay, so if you have a group G and you are given an element X, then you can consider all the powers. You can consider all the powers of that element X. So X raised to 0 is the identity element by convention. Then you have X, and X raised to minus 1, X squared, X raised to minus 2, and so on. So if you collect all the exponents of X and then denote that set by H, one can show that this set H, that is this set, is the collection of all elements of the group, which can be expressed as a power of n. Okay, one can show that this H forms a subgroup of G. Okay, this is something that you can show, and as usual, this has to be replaced by example has to be replaced by an exercise. So this forms a subgroup of G, and this is called the subgroup of G generated by X. Okay, so this is called the subgroup of G generated by X. So thus the subgroup of G generated by X is a subgroup consisting of all the powers of X, and certainly these powers need not be distinct. Okay, for example, if G is a finite group, then if you pick an element X and write down all its powers, then certainly not all of them will be distinct, because the group that you started with is finite, right? Okay, yeah, and just one more one more definition. If you have a group G, and if the subgroup generated by some element of G is equal to G itself, then you say that G is cyclic. Okay, so if there is an element X inside G such that the subgroup generated by X, that is the subgroup consisting of all the powers of X, okay, so if that subgroup is equal to G itself, then we say that the group G is cyclic. Okay, where to write? Maybe, and okay, so let me just write it here. An example of cyclic group, the very first example. Okay, so how to find examples, right? You can also ask me, okay, so the examples of group that you know. So how many groups that you, how many groups are there that you know? So first of all, you know this, this groups mu n, right? So mu n consists of all complex numbers z such that z power n equal to 1. So why don't we just try it n equal to 1? So inside mu 1, it consists of 1 only, right? You have to solve the equation z power 1 equal to 1. Okay, and certainly this group is cyclic, because if you take 1 and collect all its powers, what you get is no different from mu 1. So this is a cyclic group. Okay, another example could be mu 2. This consists of 1 and minus 1. This is a cyclic group. Okay, why? If you take 1 and take all its powers, well, then you get 1 itself. That is not equal to mu 2. But if you take minus 1 and take all its powers, you end up getting minus 1. You also get 1. So what you get is mu 2. Thus mu 2 is equal to the subgroup generated by the element minus 1. Okay, so mu 2 is cyclic. Another example could be mu 3, that consists of 1 omega square, that is also cyclic. So this is generated by omega. This is also generated by omega square. Okay. uh, yeah, I mean, if you take, I mean, if you look at the subgroup generated by omega, then that is equal to mu 3. If you take the subgroup generated by omega square, that is also equal to mu 3. Okay, so you see that mu 3 is also cyclic. So these are certain examples. Yeah. Okay, just one more remark. So the subgroup H that you see, so if you collect all the parts of a given element, that is cyclic by definition. Okay, so I'm saying that this subgroup H of G is cyclic. Okay, so a subgroup is said to be cyclic if it is cyclic as a group. Okay, and here H is cyclic because H is equal to the subgroup of H generated by this element X. X also lies inside H, right? And this is the reason for calling H the cyclic subgroup generated by X. Okay, because H is certainly a subgroup, that's for sure, and a subgroup is also a group. Okay, and H, if it is thought as a group, then one can show that H itself is cyclic. Okay, that's why sometimes H is called the cyclic subgroup generated by X. Yeah, so this is something probably I did not mention here, okay, but it was there in the title of this example, that this is a cyclic subgroup generated by an element. Okay, great. So now there are certain questions. So yeah, as you saw here, from mu1 we selected 1, and I mean, from mu1 we selected 1, and then we saw that mu1 is generated, I mean, mu1 is equal to the subgroup of mu1 generated by 1 itself. So similarly, one can ask, does there exist a group, or how many groups are there? Anyway, so let me read the question. Does there exist a group which is equal to the subgroup generated by X for any X in G? Okay, for any X in G. So of course now you know the answer. At least you know that the answer is yes, because mu1 satisfies this criterion, right? Mu1 is equal to the subgroup generated by X for any X in mu1. Okay, so are there other examples? So please work on this question. So this question now has to be a bit modified. So does there exist maybe more than one example? More than one example. Yeah, that makes more sense. Okay, well, anyway, so for example, the group Z mod nz that we have been studying for a few lectures, that is cyclic, because if you look at the equivalence class of 1 or the congruence class of 1, yeah, the equivalence class of 1 is sometimes called the congruence class of 1. So the congruence class of 1, which is the congruence class of 1 modulo n, that generates Z mod nz. You can try to write it down, okay, just to see. So you have 1 bar, and then if you add 1 bar to itself twice, you get 2 bar, and so on. Okay, so those so this group Z mod nz is cyclic, and also the group Z itself, from which we started to getting to Z mod nz, the group Z itself is also cyclic, because it is equal to the subgroup generated by the element 1. Okay, and also by the element -1, right? So if you look at the subgroup of Z generated by -1, because you have to look at all the powers. Okay, that is, you have to all the powers, so positive and negative. So all the positive and negative powers of -1, that is here. So here power means you have to compose, right? So here the law of composition is addition. So when -1 raised to n within the group Z comma plus is minus n, right? So you end up getting all the integers. So it follows that Z is cyclic, right? Here are certain exercises for you to work on. So please show that the group of rational numbers is not a cyclic group. On the other hand, you can also focus on the group of non-zero real numbers and try to see whether it forms a cyclic group or not. Okay, so please try to work on these exercises. Okay, so now here's a proposition which states that if you have a group G and X is a given element of that group, and if you look at all the integers n such that x power n equal to e, then that set of all integers, I don't know how to highlight, the set of all such integers n, that forms a subgroup of Z. Okay, that is, you're collecting all the integers such that x raised to that integer gives you identity. Okay, and that and that set S is a subgroup of Z. So this is something that we need to show, right? So first of all, note that this set is non-empty since S contains 0, right? And if you take two integers, I mean, what we are going to apply that theorem, okay? So the theorem 52, which says that if you have a subset H of a group G and if H is non-empty, then H is a subgroup if and only if for any GH inside H, GH inverse also lies inside H, okay? Anyway, so this is something that you need to show. Yeah, so you pick two elements A and B from S. So we need to look at A times B inverse. So which is A minus B, right? Because we have this additive group of integers. So we have to show that A minus B lies inside S. So we look at X raised to A minus B, and this is straightforward to show that it is identity, because X raised to A minus B is X raised to A times X raised to minus B, which is X raised to A times X raised to B whole raised to minus 1, which is identity times the inverse of it, so which is equal to identity, okay? So thus A minus B lies inside S, and by that theorem it follows that S is a subgroup of Z, right? Okay, and here is another terminology that we are going to introduce. The smallest integer, the smallest element of the set S, or the smallest, the smallest, how to say, just give me a moment. The smallest positive element of this subgroup S is called the order of X, okay? So where, this is roughly speaking, because you can observe that if you take the group G to be equal to what? For example, Z and X equal to 1, and then try to collect all the integers such that X power n gives you 0, or n times X is 0, then there is only one such n, namely 0, right? And then then there is a trouble, right? You won't get the smallest positive integer, so you need to be a bit more precise. So if you have a group G and an element X of G, then the order of X is defined as follows. So before even reading the definition, note that we have already introduced the term order, okay? But at that time we have discussed order of a group, okay? So order of a group denotes the size of the group, denotes the cardinality of that. Order of a subgroup also denotes the cardinality of that subgroup. But order of X is different, right? Earlier we discussed the notion of order of a group. Now you're discussing order of an element, right? It's customary to use the term order in both the contexts, and we do not have any choice in that regard. So, but be a bit careful. So there might be some confusions, okay? So with care, you will be out of that trouble. The order of an element X of a group G is denoted by little o of X and is defined to be the smallest positive element of S. So where of course by S the set of all integers n such that X power n equal to identity, okay? So the smallest positive element, so that you can of course pick when the size of S is at least 1, is at least 2, is larger than 1. So because inside S you have the element 0, right? So that is good. And apart from 0, if you have some integer, then you have to have some positive integer too, okay? Because S is a group. If you have some non-zero integer within S, then either that is positive or its inverse, that is positive. And inverse of that integer has to lie within S, because we have already proved that S is a subgroup, right? So yeah, so in this case you pick the smallest positive element of S, and if this is not the case, then you define the order of X to be infinity, okay? Yeah. So here's an exercise for you. Show that the order of X of an element X of a group G is equal to the cardinality of the subgroup of G generated by X, okay? So I'm not going to give you any input for this exercise right now. For Lagrange's, okay, there's an important theorem which we'll use over and over again. This is again one of the fundamental theorems that one learns in a course on groups, okay? So it states that if you have a finite group G and have a subgroup H of G, then the order of H, that is the size of H, divides the size of G, okay? So let me read it once again. To put it in words, we say that order of a subgroup divides the order of a group, okay, without introducing these letters G and H. So Lagrange's theorem states that order of a subgroup divides the order of a group. So for example, if you have a group of order 10, then inside a group of order 10, you cannot have a group of order 6, for instance, okay? So you only need to look up for subgroups of order 1 and 2 and 5 and 10, and the subgroup of order 10 has to be that group itself, right? So you only need to focus on the subgroups of order 1 and 2 and 5. Okay. Yeah. Okay, great. So now, yeah. So here is an interesting theorem which says that any group of prime order is cyclic. So why do we care for that? So the idea is to uh, classify as many groups as one can, and this theorem tells us that, or at least classify, or at least try to uh, how to say, try to establish certain common properties of all groups, or maybe a large class of groups, and this theorem is one of them. So it says that if you have the groups of prime order in mind, then any such group has to be cyclic. Okay, so it may contain 2 elements, 3 elements, or 5, or 71 elements. Okay, it has to be cyclic. Okay, yeah. So you take a group of prime order. Okay, and let's denote its order by the letter P, and we pick an element G other than the identity element, and then we look at the subgroup of G generated by the element little g. So we denote it by H. H certainly contains the elements the identity and G. Okay, and note that these two are distinct, right? Why is that so? Because G is chosen to be different from the identity element. So inside H you already have 2 elements. Okay, and now you know that the order of H has to divide the order of G. Okay, so the order of H divides the order of G, which is a prime number, right? Which is a prime number. So the order of H divides P, and you know that P has got only 2 positive divisors, namely 1 and P. So the size of H cannot be 1 because H already contains 2 distinct elements. So the size of H has to be equal to P by Lagrange's theorem. Okay, so applying Lagrange's theorem, we see that the order of H has to be equal to P, and H being a subgroup of G or a subset of G, if H has got same cardinality as that of G, then you know that H has to be equal to G. Okay, and what was H? H was generated by the element G, that it consists of all the integer parts of the element G. So it follows that the group G is cyclic. Okay, yeah. So there are a few definitions that you got to see for the first time. For instance, this notion of subgroup generated by an element, and then we discussed the notion of cyclic groups, and then and then we discussed Lagrange's theorem, and we established this nice result. So please go through these notes over and over again to make yourself familiar with all these concepts. And here are certain corollaries or exercises if you want. So it says that any group of prime order is abelian. Okay, so because it is because it consists of the parts of a single element, and more generally one can show that any cyclic group is abelian. Okay, so if you show that any cyclic group is abelian, then you know that any group of prime order is cyclic. Then combining this theorem along with this exercise, certainly after solving the exercise, you know that a group of prime order being cyclic has to be abelian. So any group of prime order is abelian. This is also not that difficult to see, but you should first solve this exercise, and then probably you just and then you have this corollary, right? We just saw right now. You start with a group of prime order by this theorem. You know that this is cyclic. By this exercise, you know that it has to be abelian. So you have this corollary. Maybe I should have put this exercise before this corollary, but yeah, this is quite elementary, but you should write down a proof. Okay, great. So we conclude here.